This is American pickup truck Aerodynamics. I'm Aiden Hanslick,
I'm Joe Borst.
I'm Adam Jansen.
And I'm Oliver Dolcino.
and we're truck kiddos.
So the test objective and key question, using a model of the best-selling truck in the US, the Ford F-150, we will measure drag to see if it's more efficient and to use the truck with its tailgate in operating position, down, or completely removed with a net in place to see which is most efficient.
So some prior
Prior,
experimentation for what's new here. Mythbusters in episode 43 did a similar test with an early model pickup truck, and they used a homemade water tunnel to visualize how the flow works with two different tailgate positions. They used oats to visualize this, and they also used real life trucks and measured the mileage at which they broke down at on the highway after they were driven identically with the same amount of gas. So in our test, we're going to make some adaptations, and we're going to use a modern pickup truck design, a 2019 F-150 instead of their 2005. And we're going to use a wind tunnel for our experimentation, and we're going to measure drag instead of fuel consumption. So a little bit about our schedule. We first off made a test plan, and then we acquired our scale model truck, which is a 1/27 scale. We ran some wind tunnel testing in our online computer simulations using ANSYS Fluent. We interpreted our results, and then here we are giving you our final thoughts.
All right, so the impact and significance of this experiment. The main impact is to increase the fuel efficiency of trucks. Trucks are already relatively fuel inefficient vehicles, so any improvement is going to be a big difference to truck owners. This has a big impact of cost savings. Gas is expensive, and this also has environmental benefits. You're burning less fossil fuels, and there's also the potential to, in the future, improve truck designs by maybe modifying the tail bed or changing things around there. So for our test plan, we ran two tests, the wind tunnel scale test and the fluid simulation. The scale test allowed us to compare the different wind speeds, while the fluid simulation allowed us to use the actual highway speeds. We tested the three configurations with the tailgate up, the tailgate down, and the tailgate completely removed. And we chose four airspeeds to represent typical driving conditions: 30 miles an hour, 45 miles an hour, and highway speeds of 60 and 80 miles per hour. The truck we were able to acquire is a scale of 1/27 size, and you can see that on the left. And on the right, you can see the truck mounted in the wind tunnel with a false floor. That's to better mimic driving conditions in real life. For the risk assessment, this experiment has relatively little risk. With the wind tunnel, it's making sure the model is securely mounted so it doesn't blow away. Earplugs and safety glasses should, the wind tunnel is very loud, and safety glasses should always be used in the lab. And we did use a cutting tool, a Dremel, to remove the tailgate for our experiment. The big thing there was to use a vise so it didn't slip or we cut ourselves, and to use the correct cutting disc so it didn't shatter when we were cutting through metal. For our budget, the truck model cost $25. The wind tunnel use was free, as Clarkson already has a wind tunnel. For the false floor, this included the poster board, suction cups, and other supplies we used to attach that to the wind tunnel. That was $15. And then the software used LabVIEW to record the data, and ANSYS Fluent to do the fluid simulations were also already owned by the university.
So the raw voltage data collected from the force balance strain gauges spans ranges that are too large to directly compare between the truck tailgate states. That can be seen here in these graphs for our 12 different comparisons. So we averaged the voltage values across the 5,000 samples we took. That was 1,000 samples per second for 5 seconds for each of the tailgate positions and speeds. And we calculated the mean drag force on the truck for each test case using a linear regression relating voltage to force. And that yielded the results shown here. The linear regression had an R-squared of approximately 1. So it was a very close relationship. The uncertainty in, can we go back? The uncertainty in each force value was determined by calculating the standard error of the voltage measurements and propagating it through the linear regression that again relates the voltage to the force. So as can be seen, the drag force increases with the square of the wind tunnel speed. That matches predictions from aerodynamic theory very well. Except for the 60-mile-an-hour data point, which is likely in error, the drag force on the truck is the lowest with the tailgate down. Leaving the tailgate up produces drag forces very similar to, but slightly higher than those with the tailgate down, and without a tailgate, the drag force is found to be the largest. On average, the drag for the model truck with the tailgate removed is about 0.36 newtons higher than for the truck with the tailgate down. Error bars are not included on this graph, as the propagated error is not large enough to be seen on the chosen axis scale.
So using engineering models, we chose ANSYS Fluent. It is provided to us by Clarkson University. Using ANSYS Fluent, we put a truck model used to model, and we modeled in SolidWorks to see how the flow regimes happen over the pickup truck and into its bed. So circled in red in the top right image is called a laminar bubble. And this is where the air holds itself in a pocket at very low speeds to no speed. And it allows for the air coming off the roof of the truck to glide over the bed instead of into it and coming off the back, yielding the most aerodynamic solution. So a little bit of uncertainty. So where could uncertainty come from? So the movement in the load cell apparatus, it's not perfectly machined to the point that there's no slop at all. So you could lose a little there. Our model doesn't have windows in the front, so there's extra drag on the truck because the windows are down compared to being on the road with the windows up at 80 miles an hour. Also, the scale of our model could add a little bit of uncertainty because we're shrinking the truck by 27 times. So our load cell combined error is about 0.5% plus or minus. And we can also look at error for used in materials and equipment.
So some difficulties encountered and lessons learned. So the scale speeds we were at were not lining up with necessary speeds required, meaning that the scale speeds to run at 1/27 scale were well above the speeds at which the wind tunnel can provide. So we just ran it at the 30, 45, 60, 80 instead of doing scale speeds, which could add a little bit of error. Attaching non-destructive false floor to the wind tunnel. So just making sure the false floor is secure and it's not affecting the load cell measurements, meaning it's separate from the truck and there's still room for the load cell to move and deflect force. Noise in the data caused by vibrations in the wind tunnel, like Aiden said, the wind tunnel wasn't perfectly machined. There's some slop in the system, and so there are some vibrations within the whole assembly. The truck model that we originally used for ANSYS, we sourced from online, and it was way too detailed for ANSYS to handle. So we had to simplify the truck model and basically create an outline in SolidWorks. And so it wasn't a perfect representation, it was an approximation in ANSYS. And we tried to source a model larger than 1/27th, but we came up short and we had to settle for 1/27th as the largest scale we could get economically. And so for our conclusion, we conclude that the tailgate up is the optimal position in ANSYS Fluent. We found through wind tunnel that tailgate down is optimal for reducing overall drag force. This aligns well with the Mythbusters conclusion, and this can be applied to other mainstream pickup truck models in the future, and we expect the same results.
Oh, yeah, I do want to save it to the cloud.